thanks for Gabriel. He made a lot of easy for me because with graphs there's a lot of recommendation systems. And before I start, I want to introduce. This is a little bit about who am I. So before I work at IBM, I work in academia. I work in the Brazilian lab. I will talk 1 minute about it. And my specific field is always data mining. I'm not from AI or machine learning. I came from AI, from databases, specifically with graph mining. So first, this year in IBM, I'm the local host of Brasis. That's the main Brazilian conference of AI. So we still have some submissions open, like ENIAC and Cademaio, and workshop on thesis and dissertation. So if you are finishing your master or your PhD, or you think that you have an interesting work, please submit. We will have a KDD competition there with real data. Will be published probably next week. And about IBM Research, so we have like 12 labs in the world. And here in Brazil, we have more or less around 100 people, half in São Paulo and half in Rio. And our main areas are natural resource solutions with oil and gas, agriculture, and mining gold. We have people from, it's not social data analytics anymore. They are working with a conversational interface, like when you have more than one bot in a conversation. We have the group of industry technology and science, and the group that is visual analytics and science, especially work on multimodal data. So why networks? Well, networks, last year I was here talking about graphs, and I was the only one in the session not talking about machine learning, even decision trees. And they asked me why not, and I say that deep learning will not solve the world problems, and I still believe this. But when you go to graphs, there is very interesting things with deep learning that I'm trying to address here. So I'm not showing any code or any results. Here's more an idea of the area and what's happened and what are the problems and what are the open problems and why this is interesting. So networks are a general language for describing modeling complex systems. So usually if you have an image or a text, you can transform this in a special vector. So you have like points. But when you come to networks, you have all these points connected. So, and we have networks all around the world. So we have like social, internet, neurons, biomedical, economic, recommendation systems, information networks, web, and so on. So, as I said, networks are the general language for describing complex systems. We share a vocabulary with a lot of domains like biological, finance, physics, economics. We have a lot of data available on the internet. So when you crawl web pages, news, links, social networks like Twitter and so on. And you can have impact like in drug design, finance, health insurance, social network, and social media. So basically, most of the tasks are about node classification. So I want to know what's the category of that node. I want to predict connections, like in social network or in LinkedIn, or which page, one page will link another, or who click or the next click. Community detection, so I want to identify a group of nodes that belongs to the same group that are connected to do like recommendation. And network similarity. If you have a drug, that's a similar drug if they have the same behavior or protein or so on. So when you have, for example, node classification, you have a network, we have label for some nodes, and you want to apply machine learning and get the predictions for these nodes. For example, classifying the function of proteins in the interactions. So we have the reference here. So when you do this, you get some labels, you get, for example, link predictions. I have the nodes, I want to predict if these nodes will be connected, and some ones it's work and others not. One specific case, this material is based from a tutorial from a professor from Stanford, like Yuri, and he's the chief scientist of Pinterest. And in Pinterest, for example, if you click in pin something, then you recommend a lot of similar pins. So this can be done by a graph. And when you have like machine learning life cycle, you have the data and structured data, learning algorithm, and the model. And you do a lot of feature engineer here, and you have like your downstream prediction task. But when you talk about graphs, especially, you want to learn these features automatically. And this is basically the big problem on graph. So the idea is how you can create a vector to represent a node. When you talk about images like very cute kittens, that is famous, or if you talk about text, you have like similar words, or you have similar characteristics on the image, it's easy. But then you talk about graphs, how can I create this vector representation embedding? So this is a famous small network in graphs, the Zachary Character Club, and this is one of the first works on deep learning with graphs, that's DeepWalk. And when you have like convolutional networks, or you have an image, you can transform this in a grid, and then you do all the process, the same with text, like the word-to-vector famous. Okay. But when you go to graphs, this is far way more complex. Why it is complex? Because you have no spatial locally like grids. So you know, no fixed node in ordering to reference certain points. So I cannot order the nodes. I have a lot of relations. And also I have dynamic, because graphs evolve over time. I have new nodes or new connections. And I have like multimodal features. So I can have attributes connect to the nodes. For example, if a node is a person, I could have the person characteristics or wishes or things that the person like, also the connections. So how can I find an embedding node to a D dimensions so that similar nodes in the graph have embeds that are close together? So let's assume that you have this graph G. We have like a set of vertex. We have the adjacency matrix. In no node features or extra information. Let's start simple. What we want to do is we want to find this embedding space. So one nodes that are similar to other, and the similar could be the nodes are connected. They are similar in the embedding space too. So our goal is to have like the similarity also in the similarity in the embedding space. So we need to define what is similarity for us. What is similar? They are connected, they are close, they have same rows, they have like same cluster coefficients, they belong to the same community, could be anything. So first, to learn these nodes embeddings, we define an encoder. So we're mapping from nodes to embeddings. We need to define a similarity function, like in the recommender systems. And you need to optimize these parameters to encode so the similarity is approximately the same in the embedded space. So actually what we will do is map each node to a low-dimensional vector. So, and you create this similarity function that will say how relationship in the vector space map in the original. So here, for example, we have matrix. Each column is a node embedded that we're learning. And this vectors indicates vectors are zero except one column indicates. So let's see. So we have this embedding matrix. We have like this embedded vector in a specific node. So one column per nodes. And dimensions of the embeddings, the size of the vector. You say like 10 or 12 or 100. So we need to define these two. So, and we have some techniques like node-to-vec, DP walk, and line. And these key distinctions between shallow methods, how to define a node similarity. So first, for defining the similarity, you need to define what task you want to do. So which is important to you? What means two nodes be similar? And this is the biggest problems with graphs, because for image or tests, it's clear for us what is similar or not. So if you look for two images, you say, yeah, they have the same draw, they have the same content, they are in the same place, they have the same colors. So it's easy to us to identify what's similar. For tests, the same thing. They have like similar words, they are about same topic, they are from the same author, or movies, for instance. But when you track for nodes, for graphs, what means two nodes are similar? So depend of the problem that you are working and depending of what you want to address. So they could be they are connect, they share neighborhood, they have like similar structure holes, they are hubs, or they are isolates, and so on. So basically, we have three main points. We can do adjacency-based similarity. We could do multi-hop similarity. And the most common approach is random walk approach. So now this is basically based on nodes. And we can spend this like for subgraphs. Instead to work a node, you can work in a subgraph. But here I am addressing only nodes. So when adjacency-based similarity. So the idea here is you have like similarity functions. For example, is just the edge weight between U and V in the network. So depend of the weight of the network, the connections between the nodes, this is the similarity of the nodes. So we have like a function that you want to minimize. So we have a loss function. So for example, we have like the sum over all node pairs, and we have like the embedding similarities, and then weighted adjacency matrix for the graph. So this is why, this is what we want to minimize. This is like the matrix factorization. Like this, I could create nodes embedded based on matrix factorizations, for instance. And when I do this, we have some drawbacks. So for example, the running time is too costly. So, because especially if my network was so big. I have like one learn vector per node, and this is consistent only in direct local neighborhoods. So the blue node is obviously more similar to green node compared to red node, despite only having connections. So we have like these problems. We have like, we are comparing nodes based in your neighborhood. When you talk about multi-hop similarity, about we have like other papers about this and are pretty new. So we are talking about the neighborhood of the node. So how much I need to walk in the network to reach other nodes. So I can consider, for instance, the k-hop node neighborhoods, 2 or 3 top neighbors. So for example, red is my target node, green are 1 hop neighbors, blue are 2 hops, and purple is 3 hops. And we have like cubic key, square and cubic key adjacency matrices. So same, I have a loss functions that I need to create to minimize this loss function. So I train the embeddings of predicted k-top neighbors. and I can use like log transformation, probabilistic adjacency matrices on the node degree, and train multiple different hop lengths and connect the output. And also I can add some bias to measure the overlap between one node and another using like Jakarta similarity or Adam-Kadar score. So this technique is known as hope, and here is then when I put the bias of the overlap measure. For instance, this is just one example I could think in other loss functions. So basically, so far, we are defining pairwise node similarity. So we are optimizing low-dimensional embeds to approximate this pairwising. What are the issues? The expensive, computationally, and must-hand design to deterministic node similarity. So here we need someone to say that, specify these functions and saying that one node is similar to another. And we have a lot of parameters like the node space. So basically, this is why random walks is a better approach. So probability that U and V occur in the same random walk. So what is a random walk? I start in a node, and with some probability, I start to visit the neighbors. I could come back from a previous node or go forward to a connect node. And then I define this path. And this path will be my vector, and I will compare this with another one to see if they're similar. So how is the probability that two nodes occur in different random walks? So it's very flexible stochastic definition of node similarity. So it incorporates both local and hard neighborhood information. So now I'm not just looking for the local neighborhood, and if I increase this neighborhood, I do not increase the number of nodes, because when I talk with hops, if I go like 3 or 4 hops, I increase the number of nodes, so I create a lot of parameters. And here in the random walk, I can travel for the neighborhood to see how I can reach other nodes. It's very efficient, so do not consider all nodes of pair when I'm training. Only need to consider pairs that co-occur in random walks. So in this optimization, what do? We do a short random walk, starting from a node to the graph and use some strategy. So I could have weights, I could have like more weight, more probability to reach that node, or they can have like the same weight and do this completely random. For node U, we collect all the multi-set of nodes that I visit during this random walking, start for 1. And then I optimize embeddings according to these functions. So now we can have repeated elements, since nodes can be visited multiple times on random walks. So to optimize this, to do better, we find embeds that minimize this loss function. And if you do this naive, you will have like high complexity. But as was said in the previous presentation, one way to optimize this is using negative sampling. So in starting, so I travel everybody, I say these nodes did not belong to this random walk, and so on. So this is, so far we have described how to optimize embeddings given random walks. And simply idea just run fixed length and bias and random walk and start from each node, for example, in this paper. So one way to improve this, so another work based on like the name, node to VEC, very similar to word to VEC. So we can try different strategies like BFS or DFS, depend of the weight. So we can combine these two based on how much I go back and how much I go deep in my network. And the BFS give like a local microscope view because they go direct to the neighbors, and while DFS go more macroscopic view because I go to other paths and go deep in my graph. So you can mix this to get different representation, different walks from the node. Depend on what you want to do. So this is one case, the Zachary Klubi data set. This is with the microscope view, so I have more emphasize and breadth first, and here the macroscopic view when you have more the DFS. So doing the embedding, how we proceed. So let's assume, so we do a neural network. So you do the network to get the embeddings. So after k-layers of neighborhood aggregation, we get output embeds for each node. So actually the neural network is to get the embeddings. And we can feed these embeds into a loss functions and run stochastic gradient descendants to train these aggregation parameters. Then we train in a unsupervised manner using only the graphic structure. So in these unsupervised loss functions, you can use like random walks, graph factorizations like matrix factorizations, and you can train the model so that similar nodes have similar embeddings. So the idea here is, as I build the node embeddings, I just say that these two nodes belong to the same community, or you'll be connecting in the future if they have like similar embeddings or they have the same classification. So this have been using some systems, like I know that Pinterest is starts to use this as recommendation system. So when you click in a pin, and then you recommend you other pin based on what you click, based on this, is the clicks are connected or not. And we have like other random walk ideas, like different of kind of bias of random walk, other schemes to optimize network preprocessing techniques. And we also can work with subgraphs. The other point is that in graphs, you can, is usually when you talk about like deep learning, and you train for instance, like for images, you put a new image and then you give like the classification of the images. One thing here is suppose that you have like a node classifications for a protein, and you train these and get these embeddings. You can use the same for another protein that you don't have the label. So if your network has the same behavior, you can use the same model. So it's pre-adaptable. And also you need to do like this distinction. So the previous techniques like adjacency matrix similarities or HOP, you need to do for every node. So when the graph evolves, you need to add the information of that node. In random walks, it's possible that you don't need to do this. So when you get a new node, you can use the other embeddings. So, but there is a lot of open problems in this field. So when you like embed nodes, so that distance embeds reflect this space similarity. So here I present you 3 types of techniques, 3 ways. But when you talk like about multimodal, for example, you want to combine content and network. So what's the best way to do? So you do one for content, you do one for network, and then combine the embeddings. We do it together. there is no right answer. So depend on what you want to do. There is a lot of open cases about this. So this is a completely open area. And we have like some methods that are better for some techniques than another. For example, node-to-vec performs better on node classification, while you have multi-hop methods perform better on link prediction. So depend of the task that you want to accomplish is the type of technique that you want to use. And random walk approaches are generally more efficient in time consuming. And you must choose the definition of any node similarities that mesh in your application. So the challenge for the future is many graphs evolve over time. So this is what, for example, social networks, there are always new connections, new people coming, new content being added. So like recommended systems, financial transactions or events in graphs, social networks, applications like prediction graph involve or anomaly detection. And about the challenges, we have like how to efficient and incrementally update the learning. So when this graph evolve, how can we update this learning representation? So suppose that you have like a random walk, and now that node now has a lot of more connections. How can you update that without need to do everything again? So how do we incorporate time? So I have this snapshot, this is the past, what's this change? How do I put this time in the network? For example, in knowledge graphs, when you have like the knowledge, if you have like an entity, a football, soccer player, for instance, that they change from one team to another. So how do you put this without forget previous knowledge? And how to forget your really irrelevant info? So do I need to forget? Do I need to, how do I address this problem? So when you come for graph, I go more or less like Eduardo said in his presentation. It's good to have a lot of data, but it's good to have good data. And more especially, in graphs depend everything how you model the problem. So the problems on graph is not the deep learning. The neural network, the convolutional network will be as we are used to have like in image or text. The problem here is how I model this information and how I create an embedding representation for the node. Could be any representation. Since this representation captures the similarity from the graph to the space that you are working. So thanks. I'll be around later. So, and if you have any questions, so please let me know.
Okay, we have time for one question.
Hi. I found the talk very interesting, thanks. About the random walk on graphs, thinking about a very nasty graph with a lot of nodes and links, how do you set the iteration number in order to cover all possible nodes? As in, the node might be correlated, similar to a lot of different nodes. You don't know how many. So after setting the path length, how many times you need to iterate the random walk in order to cover all similarities?
Actually, you don't need to cover all similarities. So you fix the path length and let's start. You can try generate other random walks for the same node. But the idea here is not cover all similarities. So the idea of random walks is that you don't need to cover the entire graph. So when you do a lot of random walkings, starting for different nodes, the idea is that because of the small world effect, you will cover a lot of important nodes. And if the node is not covered, it's because he's not really important. So this is idea why you start from, you do random walks based on very different nodes. So start from one, then start from another, and you don't need to cover the whole similarity because this works pretty well, the random thing.
Thank you very much. Congratulations on your work.
Thank you.